right, we're going to take a look at parametric functions. Parametric functions are when we have our x-coordinate and our y-coordinate, and they're defined by a third variable t. Most of the time, t is representing time. We're going to also cover vector-valued functions soon. And I guess as I've used these, they're very similar. Parametric and vector-valued functions, we're going to see how x and y are, they're both defined separately like this. And usually, the vector, they have slightly different meanings, but they're also very similar. Vector is going to be more in the application side of things, and parametric is just investigating the functions or the curves that could be created as we define x and y separately. So, let's see, do I have some questions to look at? No, we're just going to investigate them as they are. That's what we're going to do. So let's talk about Let's talk about derivatives with parametric functions. And we'll start with this one right here. So if we wanted to find dy over dx, what if we wanted to find dy over dx? That seems very reasonable. And if we want to find dy over dx, starting with x of t, that's x as a function of t, well, I could take the derivative of x with respect to t pretty easily, because I'm taking the derivative with respect to t. That's the variable that I have right here in this equation. So that would just be normal. It wouldn't be implicit differentiation, because I'm taking the derivative with respect to the variable that this is defined by. So dx over dt would be a negative sine of t. I could also find dy over dt. Same idea down here. The derivative of 2 sine of t would be 2 cosine of t. So I have dx over dt, I have dy over dt. My goal is to find dy over dx. And if we take dy over dt and divide it by dx over dt, notice if we keep change flip, the dt's are going to cancel out. And so since we found these two things individually, I can now set it up to actually find dy over dx. So dy over dx is going to be my dy over dt divided by my dx over dt. That's good. We could simplify this and get negative 2 cotangent of t, if we're feeling super good. That's a pretty nice looking answer right there. So that's the first derivative. Yeah, cool. Now I think my favorite thing about parametric functions is the second derivative, though. And why? Not dt. Why finding the second derivative I like so much isn't because the problems are super easy or anything like that, but because I think this really helps us to understand this notation. Back from when we first started talking about second derivatives, we've seen a few different ways that we can notate them, and one of them was the d squared y over dx squared. And I've always tried to give a little description as to why this is, but I think this will help us even more so to understand what's going on. So the second derivative of y with respect to x is not as simple as just taking the derivative of this again. We have the first derivative of y with respect to x. Well, I guess the better way to put that is it's not this. This is not the same thing as taking the second derivative of each of these individually. That's really what I'm trying to say. If we take the derivative, the second derivative of x with respect to t, and we take the second derivative of y with respect to t, if we were to find these things, we were to take another derivative with respect to t, when we keep change flip, we would end up with d squared y over d squared x, which doesn't have the same meaning. Because the reason we have that notation right there, where the 2 in this case is with the d, and down here, that 2 is really with the dx, the whole dx. The reason why we have this notation is because this is saying we're taking another derivative with respect to x applied to this dy over dx. We're not multiplying together the dy over dx's. We're not doing another d on the top and the bottom. We are taking a derivative with respect to x to the derivative of y with respect to x. So we do want to use the dy over dx, but we're not going to take the derivative with respect to t like we did over here. We want to take this dy over dx, and we want to take the derivative with respect to x. That's what we're trying to take the derivative of. And when I do that, I'm going to take the derivative of the outside, leaving the inside the same because the variables don't agree. I'm going to have to use implicit differentiation using my chain rule. Derivative of the outside, leaving the inside the same. Derivative of cotangent. Remember what derivative of cotangent is?
Yeah.
Yeah?
Yeah. It's negative.
It's negative.
Oh, yeah.
So the derivative of the trig functions that start with a c, those derivatives are always going to be negative, so I know it's going to change my sign. And derivative of cotangent is cosecant squared. So it has been a while since I thought about that one. But we then have to multiply by the derivative of the inside. And so we still have to apply our chain rule, and we have to multiply by the derivative of t with respect to x. Because that's what we're taking. We're taking the derivative with respect to x. So chain rule, derivative of the outside, leaving the inside the same, times the derivative of the inside. dt over dx, well, we had dx over dt. So dt over dx is the reciprocal of dx over dt. So we have 2 cosecant squared of t times 1 over a negative sine of t. Simplify that as much or as little as you want to, but that is representing our second derivative at this point. Ta-da. Thoughts about that?
Makes sense. Lots of dx's and dt's.
Lots of dx's and dt's, but I think it's always given a little bit more perspective as to the notation that we've been using. I've always appreciated it because it kind of helped everything make more sense. Including some practice work.